of flow rate. So as you can see here, we'll be talking about few different techniques. First, we'd start with obstruction meters, where if you are interested to measure flow rate in a tube or a pipe, you introduce these meters into the flow field. So that's why these are intrusive methods. So in obstruction meters, we'll be talking about variable area meter. And we also talk about orifice meter, flow nozzle, and venturi meter as part of the variable area meter. We would also talk about how one can predict flow rate by measuring velocity using velocity probes. Again, these probes are intrusive in nature. We talk about static pressure probe and total pressure probe. And then we will talk about some special methods, hardware anemometer, which has typically a very good response time. Typically, if you have flow rate varying, hardware anemometer becomes very useful as compared to the other devices that we have just noted here. But this is intrusive because you have an anemometer which needs to be put into the flow field to measure the flow rate. Then towards the end, we talk about some of the non-intrusive methods of flow rate measurement, namely the magnetic flow meter, Doppler velocimeter, and time of flight velocimeter. So we will talk about these three different types of non-intrusive flow rate measurement devices. So to start with, let us talk about variable area type flow meter. Typically, variable area type flow meter look something like this. So you have a section of the meter which is, let's say, matching the diameter of the tube whose flow rate we want to measure. But then there is a slow reduction in the area, as you can see here. So the area of cross-section here at the inlet and at the station 2 are different. Okay. So let's say the area of cross-section here is A1 and cross-sectional area here is A2. So you have velocity, because the flow rate is same, since the area of cross-sections are different, the velocities are also going to be different, right? So velocity here is V1 and velocity here is V2. But area times velocity, which is basically the flow rate, A1 V1 will be equal to A2 V2 because both are seeing the same flow rate. Now, if we apply Bernoulli equation between station 1 and station 2, we know that from Bernoulli equation, the pressure head plus velocity head plus the datum head is constant. And let's assume that station 1 and station 2 are in the same datum. That means the vertical height of these 2 points from any reference line could be the ground is constant. That means you can get rid of the datum head. So you have P1 over rho plus V1 square over 2 is P2 over rho plus V2 square over 2. Now this neglect of the datum head can be ensured by properly designing this variable area flow meter and installing in a actual pipe whose flow rate you want to measure, right? So if the pipe is horizontal, there is no problem. You can just stick it in and horizontal, the datum here at station 1 and 2 will be equal. But if it is a vertical pipe, then you have to have basically 2 90-degree bends and you introduce, still you can introduce this variable area type flow meter in a horizontal configuration, so that your station 1, station 2 datum head are going to be the same. Now, so when you write down Bernoulli equation here, the pressure head plus velocity is constant. So you can write the pressure difference between station 1 and station 2, P1 minus P2, can be written as rho by 2 into V2 square minus V1 square. Now, if I substitute for V2, so here you can see A1 V1 is A2 V2. So V2 will be A1 divided by A2 into V1. So if I substitute for V2, then I get, so now you have V1 square here, V1 square there. So V1 square comes out. So you have half rho V1 square whole into A1 over A2 whole square minus 1. So now you can solve for V1. So V1 will be basically 2 will go here. So you have 2 into P1 minus P2. Rho will come down, square root of that, because this is V1 square. And then square root of this goes to the denominator on this side. So 1 over square root of A1 over A2 whole square minus 1. Okay. So this is V1. Now if you multiply by A1, you get the flow rate. So the flow rate is basically A1 times V1, as you see here. And A1 V1 can be also written as A2 V2. Right? So if you know V1, you can find V2 in terms of A1, A2. And if you multiply by A2, that will be A2 into V2. So there are different ways. Either you can multiply A1 with V1 or A2 into V2. Both will give you the flow rate Q. Okay. Now, if you know the flow rate that is happening through a tube, you can find out the mass flow rate, which is basically density times the volume flow rate. So if you multiply rho, there is another rho here inside the bracket in the denominator. So if you multiply rho, it goes inside the bracket, becomes rho square. So rho square and this rho, one of the rows will get cancelled. So you have A2 divided by 1 minus A2 over A1 square into square root of 2 into rho into P1 minus P2. So this is basically the mass flow rate. Okay. So that means if you can design a variable type area flow meter where you know precisely what is A2, and you know, and you have a pressure measuring device like a manometer, where you can measure the delta P between station 1 and station 2. So you know P1 minus P2. You know the density of the fluid. And you know the area of cross section here and here, A1 and 2. So you can very well find out the mass flow rate, okay, or the volume flow rate. So all you need to do is basically introduce this variable area flow meter into the pipe and measure the delta P between any two sections of this meter. So this assumption, I mean, here when we estimate the mass flow rate, volume flow rate in this way, makes an important assumption that the pressure drop between this station 1 and station 2 is only because of the change in the cross section. But in reality, when you do experiment, the pressure drop can not only be because of the area change or the corresponding velocity change or the kinetic energy change. It will also be because of the viscous loss. Because the fluid has viscosity, there is going to be finite viscous loss between station 1 and station 2. But this procedure does not include for the viscous loss. Okay. Now this viscous loss, effective viscous loss, can be accounted by introducing a correction factor to the expression of flow rate or the mass flow rate. And this correction factor is known as discharge coefficient. Okay. CD is known as discharge coefficient, which basically represents the effect of viscosity or the viscous loss, which has gotten neglected in the procedure that we have used, simply using the Bernoulli equation. So you can define another parameter here in this equation, which is 1 over 1 minus A2 over A1 square root. That is known as velocity of approach factor. Okay, how much different the A1 and A2 are is represented in terms of what is called velocity of approach. So you can write Q as CD into A2. Okay, CD takes care of the viscous loss, A2, and this 1 over this term can be written as the velocity of approach factor, which is M. So CD into A2 into M into square root of 2 into P1 minus P2 over rho. Now, the product of the resistance coefficient, which takes care of the viscous effect, and the velocity of approach factor, which represents how much different the areas A1 and A2 are, this product of these two is known as flow coefficient K. So an alternate way of representing Q is basically CD into M, which you call K. So K into A2 into this term, square root of 2 into P1 minus P2 over rho. Or the mass flow rate will be simply, so rho you have to multiply here. So you get K into A2 square root of 2 rho into P1 minus P2. Now this coefficient of discharge CD and the flow coefficient M depend on the type of variable area device. Okay, because depending on the type of variable area flow device, A1 and 2 can be significantly different. And depending on the Reynolds number, your pressure loss can be different. It will not only depend on the viscous effect, but also there is going to be something called the geometry dependent viscous loss. Okay, where if you increase the Reynolds number, the vortices and the circulation is going to be very strong. That will bring in additional pressure loss. So these effects are going to be, as I said, depends on the type of flow meter, variable area flow meter that we talk about.
Sir, I have a query over here.
Yeah.
If you go to the first slide that you have shown, sir,
Okay.
here we have changed that like area, like giving a very nice radius and all between two parallel lines.
Yeah.
Right, sir? And
Yeah.
because of this, if my understanding is if the V1 is very high, then the eddy current loss will be like eddy flow loss will be very high in this bend area.
Yeah, you will have typically these eddies, these are recirculation zones around somewhere here.
Right, sir. So wouldn't it be a better design that if you just make a taper, like what I mean to say, straight face and coming down to the V2 in that way?
See, the problem is, if you use a taper design, then see, why you want to have a reduction is that you want to have an appreciable pressure difference between P1 and P2. Okay.
Right,
if
sir.
you make a taper and let's say the pressure drop is not very significant, then the problem is smaller flow rates you cannot measure with suitable accuracy. Okay. So that is the reason a sudden change in the area is preferred. But if the change in the area of section is sudden, there is going to be losses associated with that. So the tapered arrangement, the problem is that you are going to connect the tube at this end also, at this end also. Now, if you make it tapered, then from the tapered, then suddenly the tube diameter will come, right? Because the way they install this variable area flow meter is that they cut the tube in certain section and they introduce this device there, they install this, right? So now,
Right, sir.
if you make it tapered from here to here, there is going to be suddenly, there is going to be a change. And but here, you are going to have a variable area so that the delta P here is more significant than the losses that are happening at the ends. Okay.
Noted.
So that is why you use this kind of variable area flow meter.
Thank
So
you.
this is this one of the simplest type of variable area flow meter as far as fabrication is concerned. So what you do here is, this is the tube in which some flow is happening and you want to measure the flow rate. So you basically cut a section of the tube and you introduce this variable area flow meter called orifice plate. Okay. And this is typically a thin plate of suitable material, typically stainless steel or nickel or titanium. And you see that suddenly from a tube diameter D, this is like a plate of the outer diameter will be same as the ID of the tube. And then there is a smaller diameter here, okay, D. So D is smaller than the capital D, the tube diameter. So it's like a circular plate with a hole at the center, okay. And this hole that you make at the center or the orifice can be characterized in terms of what is called the diameter ratio or beta. Okay, so beta is the diameter of the hole or the orifice divided by the tube diameter. Now, there is a reason why this orifice plate have a diverging slot, not just a straight slot. Okay, so this is a divergent slot to basically minimize the kernel losses that happens here. If you make it straight, the losses will be very significant at the downstream kernel. Okay, so that is why they make this, diverging. And so you basically insert this plate there. And next thing is, because there is a sudden change in area, there is going to be a large pressure difference between the upstream and downstream of the plate. But the question is, where do you really measure the pressure? At what location upstream and what location downstream? So there are various pressure tap arrangements that are used. And one common type of pressure tap arrangement is basically called D/2 arrangement. Okay, this is most commonly used. So in this arrangement, what you do is, this is basically the orifice meter. You make a hole in the tube about distance D upstream, D being the diameter of the tube. And in the downstream, you make a pressure tab at about D/2. Okay, so you have one pressure tab here, one pressure tab here. And this could be connected to the both ends of, for example, a U-tube manometer. Okay, to measure the delta P. And there are other arrangements also. There are flange types. So here you can see in the flange type arrangement, it is about equidistance from the plate, about 25.4 millimeter upstream and same downstream. And you can also have Carnot tap arrangement where the holes are just right besides the plate upstream and downstream. So when you have a orifice plate installed, you are going to have a pressure drop, but you are also going to have losses because of viscosity, because of the formation of eddies and so on. So those effects are taken into account by this coefficient of discharge. And for orifice flow meter, this coefficient of discharge is a function of the area reduction, that means this beta, which is D/D. And it also depends on the Reynolds number based on the tube diameter, as well as the locations of these pressure taps. Okay, for example, here, beta is talking about D/D, and Reynolds number based on the diameter is here. And in addition, you have parameters L1 and L2. L1 is basically distance of the upstream pressure trap from the upstream face of the orifice plate, that is upstream face, divided by D. That means if you take a corner tap, then L1 will be 0. If you take a flange tap, it will be 25.4 millimeter divided by the diameter D in millimeter. If you take a D by 2 arrangement, then L1 will be simply be half. Right? D divided by D will be equal to 1. So L1 will be 1 for a D by 2 arrangement. L2 is the distance of the downstream pressure tap from the upstream face of the orifice plate divided by D. So again, for a corner tap, L2 will be 0. For a D by 2 tap, L2 will be half. And for the flange tap, it will be same as 25.4 divided by D in millimeter. And this equation is known as Stall's equation. Okay, where we can, for a given orifice plate, we can predict what is the value of the coefficient of discharge.
So in that Stokes second term, it is beta square 0.1 or
Which one, sorry? This one.
Stokes equation second term.
Yeah, so this is basically 0.0312 into beta square. This is not there. This is I think this is multiplied.
Yeah, it's multiplied by 1, right?
Yeah.
Okay, got it.
Okay. So this is not the thing. So here, if you see, you have flow coefficient and Reynolds number. So you can see that flow coefficient is the product of discharge coefficient into the velocity of approach factor. And M is fixed for a given orifice design, because A1 over A2 will be fixed. So M will be fixed. Now, this flow coefficient is basically representing the effect of CD, the coefficient of discharge with Reynolds number. And as you can see that if there is no viscous loss or there is no eddy loss, then CD will have a value of 1. That means basically there is no correction. If there is no loss, there is no correction. But as the loss will be more and more, then CD will deviate from 1. Okay. So you can see that again, it is going to be a function of Reynolds number. At about 10,000 Reynolds number, again, depending on the diameter ratio of the orifice to the tube diameter, the values of flow coefficient is going to be different. When the D by D ratio is 0.75, that means if the orifice is relatively larger, of course, the losses are going to be smaller. So your flow coefficient is close to 1. Okay. But if you go for a very small orifice diameter, the flow coefficient is very small. That is showing the effect of D by D. Now, if you increase the Reynolds number, the losses are going to be more significant. Okay. Because the Reynolds number higher means the velocity is high. Velocity is high means the shear stresses are high. And so the viscous losses are high. And also at higher Reynolds number, the eddies are going to be much stronger, bigger. So that will bring in additional pressure loss. These two together ensure that as you increase the Reynolds number, the flow coefficient is going to be smaller and smaller. That means you have more losses and the correction factor needs to be much smaller, deviating from 1. And so this basically shows the geometry of the orifice plate, about this diverging plate that we just talked about. The second type of velocity measuring device is known as flow measuring device is known as venturimeter. So in case of venturimeter, you have not a sudden change in the cross section unlike orifice meter. There is a gradual change in the cross-sectional area. So what we do is there is flow coming and we have a tapered arrangement here, which is forming the converging section. But then we also have a diverging section here, which nicely matches the tube at the other end. So we have basically a converging and diverging section when we talk about a venturimeter. Now, if you talk about the venturimeter design, depending on the type of venturimeter, how it is manufactured, the coefficient of discharge slightly vary. Okay, and depending on the method, the uncertainty of the CD is also noted here. And what is important is the diameter of the section of the venturimeter and the D by D ratio, the throat to the diameter ratio, which is again depends on the type of venturi. It could be anywhere between 0.3 to 0.75. And you can see that the Reynolds number that can be measured for using venturimeter lies within a range of 2 into 10⁵ to about 2 into 10⁶. And a detailed construction geometry of a venturimeter, typical venturimeter, is shown here. So you have the diameter D, which matches the tube diameter. And the length of that section, which matches D, is about D by 4 to 3D by 4. And these are typically the ASME standard venturimeter. So, and then it slowly tapers at about 21 point plus minus 2 degrees to a throat diameter, which is D. And the length of this horizontal section is same as the diameter, throat diameter D. And then there is a slow diverging angle, 5 to 15 degree. The slow diverging angle ensures a flow separation. Okay. As opposed to that happens in case of orifice meter, there is, typically the formation of wake here. You'll have a strong recirculation zones here and corresponding losses. And that is typically avoided in case of venturimeter. So we can see here, we can have a comparison between venturi and orifice meter. And nozzle meter is where you basically have a converging nozzle and then a diverging section, no horizontal section. So this is venturi versus orifice. You can see that because the losses are minimum in case of venturi as compared to orifice, where there is a sudden change, the coefficient of discharge of a venturimeter is closer to 1 as compared to orifice meter, which is very different from 1. And corresponding flow coefficient are also equivalently different. And you can see that for a similar kind of flow condition, the pressure drop across venturi is very small compared to the orifice flow meter. Correspondingly, the pressure difference is largely different. So this is how venturimeter and orifice meters are compared. And another thing to notice here is that the coefficient discharge is varying with the Reynolds number, as you see here. So you have Reynolds number in this axis and coefficient discharge in this axis. So you can see that initially the coefficient discharge increases with Reynolds number. And this is because as you increase the Reynolds number, what happens is your flow becomes less skin friction dominant and more the form factor dominant. That means the delta P contribution coming from the friction reduces, and that coming from the sudden change in the area and the corresponding formation of eddy increases. And therefore, this coefficient of discharge tends to increase and become more close to 1. But beyond a critical Reynolds number, you see that CD takes a constant value, and which is independent of further increase in Reynolds number, where the formation of the skin friction coefficient and the formation of the delta P because of the cross-sectional area change takes a steady value. And your CD for the venturi is very close to 1, okay, as opposed to orifice meter, which is something that we discussed. Here, as opposed to orifice meter, where there is a sudden change, there is flow separation formation of eddies, here that effect is negligible. And that is why the CD becomes very close to 1. And this basically compares the irrecoverable pressure loss that is attributed to the formation of eddies, which is very strong in orifice meter. So thereby the irrecoverable pressure loss is very high in case of orifice meter and low in case of venturi meter. And this basically explains why the CD is higher in venturi and lower in orifice. Now, when you have incompressible flow, then all these formula that you have, this formula works fine. When you have compressible flow, that means you have fluid like air, and over a Mach number of typically 0.3 is considered to be compressible flow. In case of compressible flow, in addition to correcting for the viscous losses and eddy losses, which is accounted by K, you have another factor which is called expansion factor. Okay, and this comes from gas dynamics, where you talk about flow of compressible fluid. This happens particularly when the P1 minus P2, that means the delta P that you measure across the orifice meter or venturi meter, is not small compared to the upstream pressure P1. Okay, the pressure difference is almost comparable to the pressure itself. And the P2 over P1 is very different from unity. So you bring in this correction factor, and this correction factor, this is again derived from gas dynamics, is a function of the pressure ratio and gamma, which is the ratio of the specific heats, Cp over Cv. Because we are talking about compressible flows, you have gas dynamics, and in that context, we talk about the Cp and Cv, and that ratio comes here. And it is also a function of beta. Beta is basically the diameter ratio, the small d divided by the capital D. And in orifices, when you have flange taps or Benacontra taps, then you can approximate this y. So this is basically, we talk about the flange tap, and these corner taps are typically called the Benacontra taps. So when you have these taps, you can actually have a simpler expression for the correction factor, which is given here. And again, it is a function of P1, P2, and gamma and beta. And when you have flange tap, you have this expression, which is given as, again, this is a function of beta, P1, P2, and gamma. Now, if you go through the compressible flow theory, it is known from gas dynamics that velocity of a gas is equal to the velocity of sound at the throat if the pressure ratio is more than a critical value. What it is saying is that if you use compressible flow and you want to know what is the velocity of sound here, it will be same as the velocity of the flow itself when the pressure ratio P1 over P2 is above a critical value. Okay, that means this velocity becomes equivalent to the speed of sound. Okay, so this is from gas dynamics. So if you use that, again from gas dynamics, people have shown that the ratio of upstream pressure to downstream pressure can be greater than equal to this parameter, which is 2 over 1 plus gamma to the power minus gamma over gamma minus 1. Okay. Now, this P1 by P2, which is obtained from gas dynamics, if you substitute in this equation here, P1 by P2, P1 by P2, P1 by P2, if you substitute, you can show that this expression, I mean, this is flow rate, but if you multiply by density, that gives you mass flow rate. And you substitute P1 by P2 from here. And then if you do the math, you can actually show that the mass flow rate can be written as the density in the upstream side, the velocity of sound in the upstream side, throat area into 2 by 1 plus gamma to the power minus gamma plus 1 divided by 2 into gamma minus 1. Now this velocity of sound can be written as square root of gamma over r into t. This is again from gas dynamics, that velocity of sound is square root of Cp by Cv divided by the gas constant into temperature. So now for a compressible fluid, you have this expression for the mass flow rate. So it says that for a compressible fluid, you really do not need to measure the pressure at the upstream and pressure at the downstream as you do for a incompressible fluid for measuring volume flow rate, mass flow rate, because that is what this formula says, right? You need to measure P1, P2 to measure volume flow rate. But in a compressible fluid, you can just measure the pressure in the upstream channel and temperature in the upstream channel. With these two, you would be able to measure the mass flow rate, okay, given by this expression.
Sir,
Yeah.
where would I actually desire this sonic velocity and all?
So if you use, compressible flow through a tube, okay, where your velocity is very large, okay. So this may be, some kind of application requiring, large pressure of gas, okay. In various processes, right, you may need, very high gas pressure for different chemical application, or maybe some kind of application where,
Propulsion also?
yeah, you can also use for, propulsion application.
Okay, sir.
So there, when the your pressure becomes pressure ratio becomes very large, and so that the velocity matches the sonic velocity at the throat, then you can just simply use this formula and don't need to really measure the pressure upstream, downstream. You can just measure the pressure upstream and the temperature, and you are done. Okay.
So there is also a concept now, like if the velocity of the like if compressible fluid goes beyond a critical value, then nozzle acts like a diffuser and diffuser acts like a nozzle, something like that.
So we are not talking about supersonic case. We are
Okay.
only, sorry, hypersonic case. We are only talking about a supersonic case. Okay.
That
So
typically happens at which conditions? I just forgot it. It was
hypersonic, you talk about very high Mach number, typically above close to Mach number 10 or above that. Okay. So we are in the supersonic regime, and where, we only are concerned about the sonic velocity at the throat of the flow measuring device. Okay.
Right.
Okay, so now I would talk about one more flow measuring device, that is the drag flow meter, and this is also called as rotameter. So these rotameters have typically a tube sort of arrangement, and the tube is tapered tube. Basically, your inlet flow is coming here and outlet flow is going there. So this rotameter has a tapered tube, as I said, something like this. The ID is tapered. And you have a structure here. The structure is called bob. Okay. Now, as the flow rate, depending on the flow rate, if there is no flow, the bob will be sitting just at the bottom of this tube, tapered tube. Okay, and typically these rotameters are installed in a vertical configuration. Okay, so if there is no flow, then it is sitting at the bottom of the tapered tube. Now, how far this rotameter will lift up would depend on the flow rate. Because the flow rate is higher, the drag that is acting on the rotameter will be higher. So that means this rotameter is going to go farther and farther from the inlet bottom, depending on the flow rate. So the displacement of this rotameter, that is Y, will be related to the flow rate Q. Okay. And this is a particular situation where the rotameter is, has reached here because of flow. So this rotameter has a, this bob, a diameter is small d, and the tube will have a, an inner diameter which is d, same as the outer diameter of the bob. The flow area, the inner area will be basically dictated by the d, and the outer area will be the ID of this taper tube. So in this annular region only the flow is going to go. Okay, so the flow cross-sectional area will be pi by 4 dy square minus d square. Okay, so which is indicated by this ring. This ring is basically representing the annular region through which flow happens. Now, if we can look at what are the forces acting on this bob and do a force balance. First is the weight of the bob. The weight of the bob is basically m into g. The mass of the bob is density of the bob material into volume of the bob into g. So this is the weight of the bob. The buoyancy force that the bob would experience would be basically rho b minus rho f into Vv into g. So basically the buoyancy force will be rho f into Vv into g. Density of the fluid into the volume of the bob into g. So this is basically the buoyancy force. The drag force would depend on the area. Okay. So it's the surface area. Let's say the bob has a surface area of SB. Okay. And the drag coefficient is CD. And then the dynamic pressure, which is density of the fluid. The mean velocity of the flow in the annular region, Vm square divided by 2. Because the drag is acting in this region of the bob, and where the velocity is Vm. So this is basically the dynamic pressure. Dynamic pressure into the area gives you the force. And CD is basically a correction factor because you are not accounting for the viscous loss. Now, if you equate these three forces, basically because of the weight, the bob will try to go down to the bottom, but the buoyancy force will try to move it up. Then the drag force because of the fluid would try to move it up. So the weight will be balanced by buoyancy plus drag. Okay. And so if you solve this, you can find the velocity of the flow is square root of 2 into VB into G divided by CD into SB into rho B minus rho F divided by rho F square. So the shape of the bob should be chosen properly so that the discharge coefficient is not a very strong function of Reynolds number. Because if the flow rate changes and every time you have to know what is the discharge coefficient, that itself brings in uncertainty, because there will be change in the flow rate effect on the CD. That means you are measuring flow rate, but then your CD is a function of flow rate. So it becomes implicit. So to make sure that CD is minimum. And the other thing that this equation tells us, that in order to measure the flow velocity, this term is inside a square root. So this should not be negative, because if this is negative, then this becomes imaginary. So the bob material should always have a density higher than the fluid density. That means that without flow, the bob is just sitting at the bottom. Okay, that means the weight of the bob is higher than the buoyancy force acting on the bob. This weight of the bob has to be higher than the buoyancy force when rho B is greater than rho F. Okay. So as I said, the available area of the flow AF is basically pi into dy square minus d square over 4. Also by geometry, because this is a tapered geometry, you can write that the diameter of this tube at any y can be diameter at the bottom. So sorry, this should be small d. Okay. And this should be the diameter of the bob here. Okay, the pipe D diameter is capital D here, that is fine. But the bob diameter here should be small d. Small d plus 2y into tan alpha. Okay, so if you take a triangle here, this alpha is the divergence angle. So dy should be d plus 2y tan alpha at any y. And so this dy you can substitute here. So you have area of cross section and velocity, so you multiply that to get flow rate. So this area of flow, pi by 2, the small d, the diameter of the bob, will be equal to the diameter of the tube at the bottom, that is capital D. So that is d plus 2i tan alpha whole square minus d square. So now if you take square and you adjust the terms, you can show this as pi by 4 d square minus d square plus pi y into d tan alpha. So flow rate is basically Vm into F. So you multiplied Vm already, you have found from here, force balance. Sorry, you have AF from here. And if you multiply, you get the flow rate. Okay. Now, if your D becomes equal to D, you can design this, right? So then this term vanishes. So you have flow rate can be simply pi y d tan alpha. So pi into d tan alpha can be written as k. Okay. And into this term, it can be written as k. So q will be some constant times y. Okay. So this validates our hypothesis that as the flow rate increases, the position of the bob would increase linearly. Okay. And this k is dependent on all the parameters here except, so this term goes because you can design the bob diameter and the tube diameter at the bottom to be equal. So they vanish. So you have the remaining terms, and the remaining terms are basically k. So which is 2 into VBG CDSB, this term here into pi d tan alpha. So that means you can have a linear scale here. That is typically in an actual drag flow meter, rotameter, you typically have a scale here. And these graduations on the scale are calibrated with the flow rate. So depending on the bob position, you can directly read the value on the scale and you convert into equivalent flow rate that is happening through this rotameter. So that is how rotameters work. Okay, so I will stop here. If you have any question, we can discuss.
Recording stopped.
Sir, when will the results of the exam be given, sir?
Oh, the midterm exam?
Yeah.
Yeah, I would do that carefully. Yeah, maybe I would take some more time to do it. I would definitely do it before the answer. Maybe I would try to finish it within a couple of weeks. It's more difficult to, correct the online version. So need some more time.
So you get a hard copy of this thing, yeah, or soft copy only?
No, only soft copy.
Okay, okay.
Sir, just want to know how the further classes will grow. Will go actually yeah, we are covering the venturing meters now. So orifice meter and everything. And what will be the upcoming sessions? Will
We
be
are
there?
going to talk about velocity measurement device, and then we are going to talk about some miscellaneous property measurement. Okay. And then maybe we can have some problems I would solve from different portions. And I think with that, we would wrap up.
Okay, sir. Okay, yeah, thank you.
Professor, one request I have, of course, it's not the scope of the syllabus, but that the flow through it like tube in that sense, okay, where we define the various parameter like Prandtl number, Reynolds number, all those things. So, if you can give some reference so that we can refresh our basics, because these things are very well heard, but
okay, Reynolds number, etc. You want to talk about the Prandtl number and
all right, sir. Just a 15-minute session from your side. It will refresh our
so
memory of.
You want me to, take a class to discuss about those things in detail?
It would be a very a generous approach, sir. But if you don't have time, then we can also refer some books.
Okay, if because see the final purpose is to maximize the learning. Okay.
Right, sir.
Just covering syllabus when you want to learn something, doesn't help. So if you really want us to and me to do that, then we can do that. Let this pressure measurement be over, because I don't want to take a break in the middle.
Sure,
so
sir.
let this be over, and then I can take maybe one class or whatever more required to cover up some of the basics that are related to understand these things.
Yeah, that will be very insightful. I think the team agrees probably.
We'll do that. We'll do.
Thanks.
Sir, for the final semester, is it open book or closed book test, sir?
We have done the mid-sem open book, open notes. Not book as such.
Oh, sorry. Yes, yeah.
We'll have the same in the mid-sem.
Okay, sir, yeah.
But do you prefer a closed notes?
Sir, we'll fail, sir. I'm sure about that.
No, see, we don't do that here for IIT students, regular students here. But I understand the challenges of,
It's a very, I would say, it's a very tricky concept and very interesting subject. So, but the thing is,
it's fast actually. The measurement, the problem
exactly,
is we're almost covering, everything starting from heat transfer to fluid mechanics to, measurements, statistics, and various concepts are coming. So it becomes tricky, but I mean, that is how things are, right? I mean, we need to. So if you need, I mean, as you said rightly, these some of the basics of flow and maybe heat transfer. If you want me to cover, you have asked for it, we can do it. Okay.
So yeah, means for this, we need to go with the open book because equations are very difficult to remember.
Yes,
It's very tough for
yes.
us.
We would do open book. I mean,
Sure,
whatever
sure,
you
sir. One more request from our side, means from my side, I mean, I'm not sure about others. Will it be possible for you to share the slides earlier to the classes, sir, so that we can refer it?
You see, the problem why we do not do, I mean, at least for regular IIT students, is that they bunk classes. Okay. So I think it is a better practice. This is something that I have been following even for industry students in earlier years, that maybe I'm not more regularly sending. So what we can do is, at the end of every week, I should start sending. Maybe before closing on the Wednesdays, I would start sending you, the slides for that week. I think probably that's something you can do.
Yeah, sir, that works. That would be.
Or before I take the class, I send you the lecture and then start doing the lecture. Okay, we'll figure out. We'll do something to make sure that the slides are with you.
Thank you, sir.
Okay, thank you. Thank you very much.
Thank you, sir. Thank you very much.
Thank you, sir.
Yes, yes, sir.